postdocs as assistant research scientist at Arizona State University. I did my PhD from Arizona State University too, under the guidance of Professor Narayan Naithilat. I'll be like in this one, I'll be jumping between slides and app and this and that. It will be a, I hope it's not as big of a mess, but again, I'll try to do it as easily as possible so that everyone understands. We'll not talk about much in terms of like what packing is, what aggregate gradation does, because again, from the morning, I think the maximum thing you have seen till at least lunchtime is like packing, packing, packing. Aggregates gradation, good gradation gives you good packing. You require less space, you require less water. What I'm gonna show you is like again, it's not gonna be that much of a detail, but it's like we are developing this app. Is the things that I show you today will help you use this app in future if you need it. Because again, there's few things that you have to learn, like how to use, like how to create the input files and all those things. I'll show you where the apps are at. I think like we send a email out to everyone to download. I know like some people were saying it's taking a lot of time to install some of the apps. I'm not an app developer, so whatever I could do my best, I tried. So in future, if I can, I'll try to optimize the installation time for those two. So to get started with, again, the importance of packing in rheology, and as I do 3D printing a lot, it does have a lot of importance in 3D printing itself. Like a certain mix where I'll show you later on, like I'll show you two different mixes that we print. One is a complete cement based mix that we print at zero point 0.4 water to binder ratio for that, and L30 mix, like a 30% limestone mix, which we print at 0.35 water cement ratio only, water binder ratio only. Again, this all goes down to like the packing, the actual gradations of particles that are present in the system. So it basically changes the amount of water required also. All those like packing density, the graph you saw, like there are certain particle size distribution which you use, you will get a very maximum packing density. After that, it again comes down. I'll not talk about basically optimizing. I'll show you slight things with aggregates, how selection of different particle size does to the fraction to be higher than selecting a very random larger particles. So to start with, the main software will be this. I hope everyone has downloaded it. Sorry that we don't have this for Mac users, because Mac requires us to be a actual professional developer to actually give you out an app, which we are not. So we don't have this for Mac, but we have it for Windows. Again, in Windows also, like you can Mac also, you can download Windows as a separate part and you can use it if you want, or you can use a Windows PC. Hopefully, most people do have Windows. So if you have already gotten the app, I don't know if you have extracted it, but I'm just gonna show you if somebody has not done. I'm just gonna go quickly over it. If somebody's stuck in the downloading part, okay. So because it's in Google Drive, you just have to give it a access saying that it does not have virus. We can nearly 95% guarantee it does not have virus because we developed everything in our place, so it should not have any virus. Just do download anyway. Once you get the download, once you extract all, you'll see inside the folder, you'll see this hydration desktop.exe. You don't have to install this. You directly get this. This is gonna be one of the software. Like this is what you are gonna be using here. Again, when you run it, window protects it because again we are not registered developers, so they think that it's a malicious software. You don't should not run. Just click more info, and you should get run anyway as an option. I hope nobody's having problem till this point, right? So this is the software interface. The things that we have will have in future is that I had this highlighted. Oh, I think I had this highlighted here. But like we have three different menus. The build MS is the one that generates the microstructure. The second one, that's the distribute MS, is once the microstructure is generated. This again, I was talking outside also. We plan to develop this as a microstructure generation and then use it for cement hydration. So, is there an issue? Are you guys having trouble to install or something? No, right? Okay. So once we develop the microstructure, again, the way you see, right, the particles are there, waters are on the pores. So these waters hydrate the cement particles. So you can actually simulate hydration in cement. Right now, the app, this part is still under development because for some weird reason the distribute ms is not giving us the output file. We have to go back to and check the code because what it does is like once you have the microstructure, distribute ms basically separates out your all the phases inside even each particle, so that actually the hydration phenomenon, the actual chemical reaction that we are giving it to it, like water is touching the particle, right? So it should hydrate a certain way. For cement it should hydrate a certain way. For fly ash, for limestone it should be slightly different. So those kind of things this distributed ms does, but again we are not getting any output from this file, so we will only stick with build ms for today. So for build ms, if you see there's a choose.dat file, so that's where it goes down to, like, again you will have to type in all the values. So we try to rather make it as an input file where instead of typing each time you can actually generate it. And we have, like, I'll show you how we use generator input file. But what this that file takes is actually the particle size distribution of different particles. Like let's say you have opc in the cement in the system, then you will have the particle sizes of OPC, and you'll have like certain radius particles, this many numbers based on how much volume percentage of each size is there, depending on the PSD. Like for different, like you will have to discretize this into certain particle size and the volume percentage. You should understand that this is cumulative, while this is not cumulative. This is just between two particle sizes. We are saying like if you had a 0.159 sieve and 178 sieve, 159 will retain 0.03 percentage of the total, while 0.178 will retain 0.04 percentage. I'll show you down the line also, like there is a list of shifts we have for most of the things. We have few of them already done, and we have like them defined in the system. So it's basically define the proportion. Now the next thing goes to like defining the proportion of the mix. Like what do you have in the mix? Do you have 70% cement, 30% limestone, or you have 100% cement? Because that basically determines how many different kinds of material you have. Again, that will come into picture later on because we distinguish each particle as a material. We will distinguish cement to be cement, limestone to be limestone. For particle packing, it does not matter for us to distinguish between those particles. But if we have to use it further in hydration, we need to know which particle is what, because we can't ask limestone to hydrate like cement particles. So for those reasons, we have it distinguished in the system. So again, as a general start, we'll see it in terms of the distinguished particles, so that later on, if it develops further and when we have the hydration, at least you guys know how to reach to the microstructure and basically start the hydration scheme. And the other component is like water cement ratio. This again, you can go get away with not defining a water to binder ratio, because again, if you want to just do packing, it's fine. You can just use the particles and select higher packing fraction till you reach a certain position where the software is gonna say like I can't distribute this pairs now, meaning like you are like at the limit of heterogeneous mixing. Like basically it's a random seeding of particle that it does on a certain volume. So the software will say at a point that okay, I can't distribute this pair, meaning like there's no space for the pair to be distributed. So that's what the maximum packing you most probably will end up getting. So if you have a water binder ratio, I'll show you in terms of water binder ratio how we calculate all these values in the next slides, because pores are required. Like now you can't have a maximum saying like let's say you have 40% is water, then you can't go to a solid volume fraction of 70. That's that 40% you need for water also. Again, there are air voids, different things that get basically when you mix, air voids do form. Again, if you want to account for that, again you will have to put 40 plus the air voids percent and basically select the rest as a solid fraction. Now, again, it does not matter for the distribution, but it will matter later on when you do hydration, because you want to have as exact of a microstructure as it could be in the system. Because if you have let's say 7% porosity, you want to have the system such that there's like 40% for water, 7% for porosity, and the rest for solid. So those kind of things will be defined. Like again, you as a user will be defining this. So to look at the steps onto what happens and how we do it. So initially we started with the particle size distribution and a volume fraction, right? But because like there will be like 10 to 20 to 50 to 100 different sieve sizes that we can distinguish it to, what we basically do is like we calculate an equivalent volume and we basically shrink everything back down to 2 micron size. Again, you could end up doing like a 2 micron sieve, 4 micron sieve, 6 micron sieve, 8 micron sieve, and actually use the volume percentage as such. But again, it won't be correct that way because let's say you have a 0.02 micron sieve size, right? The volume percentage actually will not be like directly replicated by 2%. So you will have to calculate an equivalent volume. I thought I had the equation there, but again, it's basically like, okay, you have a certain particle size. You are trying to say like, okay, I now want this to be a 2% one. So I'm calculating a volume percentage, equivalent volume percentage, which I have an Excel sheet that I'm gonna kind of try to work with you guys to show that how it actually goes. I'm just giving a brief overview right now, so that when I actually show the Excel sheet, it does not become like, oh, what are we doing? So just to show what goes to the Excel sheet, I'm showing you this. So once we put a equivalent volume for all this, we do a cumulative volume, meaning like anything from 0 to 2 goes to a 2 micron bin, anything from 2 to 4 goes to a 4 micron bin, and so on. We can keep basically do that. And for this, as I said, like this first example that I have in the slide is for a OPC 0.4 water binder ratio mix. That basically that 0.4 water binder is by weight. And when we convert it to volume, it goes to like 0.56% volume of the mix, which means like we have like about 0.44% of the volume remaining. So that's like, if you say you don't want, you want zero porosity, that's the maximum you can go to. So again, I'll talk to you about this later. This will be like a recap when we go to the Excel sheet. There's a selection point where you can assume a particle for volume fraction initially. So for the exercise, this exercise, I started with a 0.44 packing fraction assumption. That's the maximum. I started with this because the end product usually becomes lesser than what we actually assume there. It's either equal or lesser than that. It can't be higher than that. So for this case, when I assumed 0.44, we ended up with, I think it's in the next slide, but with, yeah, I think it's a zero point 0.2 is what we theoretically calculated, and the software does a 70% porosity. But with that, the next thing is to like, now we have volume percentage, right? Equivalent volume percentage. So we can't put equivalent volume percentage. We have to put equivalent number of spheres that take that volume. So calculation procedure is again involved here, where it's nothing else than like the total volume times the packing fraction that you assumed, meaning like you have a 100 meter cube volume, then only 44 meter cube can have solid, which basically is the proportion of the component used. Here it's only OPC, so it's 100%. But let's say if you had OPC and limestone, you have to distribute it between OPC and limestone, right? So that goes into the equation. And then cumulative volume percentage is for the certain size. Now you can do 40 meter cube out of 100 meter cube. But in that 40 meter cube also, the 2 micron cannot take all the 40 meter cube. So 2 micron again needs to have a certain volume percentage. That is like the equivalent volume percentage that we calculated here. That's the maximum volume it can take. So what we do is like we calculate the cumulative volume percentage. And again, this is something that is like a more of an image generation thing, where because you can generate different kinds of image. Here we are selecting a 100 by 100 by 100 pixel image. And the pixel has a volume, like the way you have a volume for your material, the pixelated image also has a volume which is called voxel. So this again, I'm not going to go a lot in detail into the pixel volume, but we have it set up in the Excel sheet right away for the ease of use. So once this is done, you get the number of spheres that you get from the Excel sheet. Like these are the numbers of sphere that the software has to try to distribute. So with that, once you have the number of volume, again, because you have now number of spheres, you can calculate the volume. You can calculate theoretically what the packing fraction should be. It always comes out significantly lesser than it actually is. So you see the picture, right? Like you selected a particle volume fraction, you ended up with a theoretical volume fraction, and the software does the distribution and gives you a volume fraction. Like again, I'll show you why it's 70% instead when you selected actually 44. So maximum should have been 56%. Why it goes to 70%? I'll talk to you once I show you the examples. But like for this case, like once we did all this, we saw that the porosity goes to 70%. Means like we most probably have more space to keep more OPC particles in the system. So what we can do is like now we change the assumption to a higher particle fraction. So with trial and error, a point, oh, I think this is wrong. 0.65 is what we selected. For some reason, it's 0.4 here. So we said I selected 0.65, which basically gave a theoretical value of 0.3. And when I actually run the model, the microstructure distribution model, we get a 58% porosity, meaning like 56 to 58 is like nearby enough. And I did not go farther than this. Like if I would have selected 0.66, maybe it would have been 57%. But again, you get the picture, right? Like you have the selection criteria. Like you can select the values to end up with what you actually need on this case. So for this, again, these are the calculations for this value. I have the, these are, I think this is example one and example two on the example list that I have. So we'll talk about it further in there. But like again, these are the volume fractions, right? If you see repeatedly, I'm giving you in a ascending order, right? But the thing is, the input file takes it in descending order. And descending order itself being like now I'm talking to you in terms of one single particle, OPC. Now, if you have limestone, the descending factor comes for limestone too. Meaning like if you have a 18 micron OPC and 18 micron limestone, you have to select the OPC first, then limestone. Because what the software does is like it randomly sits play points in the voxel to basically have the particle there, meaning like it starts from the largest particle. Because if you have seen there's a very good YouTube Instagram reel kind of video where the professor shows like, oh, you put aggregates, you put sand, and he ends up saying like you always have place for two bottles of beer with friends. So that kind of scenario where you actually have to put the larger particle first, so that if you put the smaller particle first, the gap might not be enough for the larger particles to sit in. But usually if you have the larger particle already in, there should be some space for the smaller particle to be distributed. So it starts with the larger particle first and then keeps on distributing the smaller particle. So it goes descending order, not ascending order. So now we have to change the whole thing into descending order. And the other thing is like now is like it has a row input. I'll show you in the next slide. It has like yeah, so this is the kind of input it takes. And this is the file that gives you what to do. But again, we have simplified it further, but it basically requires you to put the radius number of spheres, the radius of spheres, and what material it is. So that needs to go in descending order for all the particles. And again, to distinguish between particles, we have in the system, like I think I have not made a README file for this. I should make one README file where we have each number given for material. Like if you have a material one, it's cement. In cement also, once you distribute it C3S, we distinguish it as C3S, and 1, 2, 3, 4 basically belongs to cement. 5 belongs to gypsum, 6 is hemihydrate, 7 anhydrate, 8 pozzolanic material, and we have like about I think 15 to 20 materials already defined. And obviously we can define more. We can define furthermore. Again, we need to slightly add to. I think one thing that we do not still have is microsilica, which we should define. Neither then we have most of the generic materials defined, like inert materials, aggregates, other like flat aggregates kind of thing also. So these again, like these are basically for the system to know what actually the value is at. I'll show you once I go to the actual Excel sheet. I'll show you 4 different materials that I select for the examples. I'll most probably not go into all 4, but for the sake of, but initially for microstructure, I would say like it does not matter. If you select one for everything also, it will give you the microstructure. Later on, if you want to do the cement hydration model when it is developed, obviously you can't do that just by selecting one, because it will think that the limestone is also cement. So this comes into picture for hydration, while for the microstructure distribution, there's no issue with having all the numbers same. So you see these 3 things, right? We have to have those in sequence. And again, the program itself has few things as like menus to select. Like there's a menu 2 selected for it to start distributing the spares. There's a menu 4 selected for it to actually output what the porosity is, what the solute fraction is, and all those parameters. There's another input where I think it's 5, which basically prints all this result into a file. So me trying to tell you all this and trying to somebody trying to understand it might be very confusing if somebody who developed it already does not tell you. Even with readme it's going to be slightly confusing, so I'm just gonna not brush up on this that much. But the thing is, like, there's one thing, like how many different types of particles are there. This is very small. I will see the excel also, so you will have a chance to look at all this again. But like there are 17 different kinds of particles I just defined here. And these you see, like, it's number of spheres, radius of sphere, phase of the sphere, and then again number of sphere, radius of sphere, so it goes on descending order. So now we're trying to ask user to actually create this is a issue, because once you understand it, it's very easy. It does not have much, but there's a high chance of making error, right? So what do? We created an Excel sheet for this also. So I'll most probably jump between this Excel sheet to show you. So this is the first Excel sheet we had, where you have, like, basically, if you see, everything is defined on the right, what actually is numbers mean. But again, you have to follow this particular pattern to fill up all the numbers. And again, let's say if you have, like, say, instead of, I think this is defined for 15. Now, if you have 17, you have to add three more for 16, three more for 17, which again, user has to understand to do that, right? Neither then this will be like somebody who has 17 particle and they can't do it. So this is again something we had. The next thing that we now have, I hope everybody downloaded this. Uh, there's a different Excel sheet with the examples sheet. There's two Excel sheets within the examples also of the same thing, because I did not want to jump between too many things, so I put that there. So I think I'm just gonna go back to the presentations to show you a few things. Like the Excel sheet are color coded, meaning that anything green, that is what the user should play around with. Like a user who wants to actually run a model should only touch the green colored things. Now again, if you select to change the color yourself and it does not remain green, does not mean you don't use those, right? So anything red is something, unless you know what it is doing, it's better you do not touch it. Anything that's green with a background yellow, and this is just for the pixel volume, which again, for the chip size that I have already defined, we have few between chip size that are missing. Like we don't have, I think we don't have 10, no, we don't have 12, 18, something like those. Like the bin size, we have everything in the increment of 2, but there are 2 4 chip sizes, because when we did it, there's nothing written on it, so we never have the chip sizes on the x-axis, so it never, like anything between 8 and 10 is not there, then it's not gonna, this Excel sheet is never gonna give you a 10 size, because this is developed such that if you input something that's within 8 and 10 is only when it's going to create 10, because if there's 0% volume it will just ignore 10. So that way, that's the only place you might have to check. And how to check that is again this, like we already have the 2 to 50, I think we have from 2 to 50 we already have the pixel volumes in the Excel sheet, so you can just use that pixel volumes. Again, this whole sheet is red because it's not useful unless you have to exchange it to the actual cells. And the folder itself has like a, the Excel sheet basically at the end of it. I'll go through the Excel sheet now after this slide. But the Excel sheet at the end gives you a row of material parameters based on all your inputs. It's like based on your input. So if you have 17 things, it will give you a 17 already developed column. If you have 5 only, it will develop for 5. And I have, like, I when I made this slide, I had only 8 examples. I think now I have 14 examples or so already in the folder. So at least initially I had 8. So I have written 8 there. So to go to the Excel sheet, so let me walk through this with you. So this again, as I said, it's a pixel volume thing. So you do not touch it unless it's required later. I will tell you where it's required. So this, to make it more simplistic, I have the mixture definition also here, so that you can define actual mixture here, so that you don't have to worry about calculation. Like you have, again, I have developed it for only 4 materials. I again, in Excel sheet, defining for and material is a problematic thing, I would say. So I have defined it for 4 materials for now. But let's say in the top left, if you see, there are few green cells. Should I increase this? So for few of the things, I already have the specific gravity defined. This specific gravity is defined to calculate the volume of the material. Like again, few people do it volume based, few people do it weight based mixing. We usually tend to do mass proportioning. So all this percentage proportioning are mass proportioning. It's not volume proportioning. So you can actually type in, like again, I have not defined it as cement or anything because again, material one can be anything. So for us, because I have the 3.15 there, that's cement. And that's why I am writing it's OPC. This is limestone, this is fly ash, this is inert. The inert is not actually inert, but I have it as inert because I had a particle extra that I wanted to show you for just to set up example for a different particle size. So right now I have it set it for 100, meaning like this is the 100 and zero point 0.4. This is example one that I already have set up. Like you have the input file already. What I'm trying to show you is like how that input file is generated. So once this is there, the Excel sheet does the volume calculation. And if you actually go to material one, then you can see this system size is that 100 by 100 pixel that I defined. Now it does you the volume based calculation for water, meaning like you should have 0.55%, 55% volume of water occupying the volume. Means the maximum you can have is like 0.44, meaning 44% can be solid initially, assuming there's no porosity. Now if you have pores, that's a different story. So, and this 0.65 is again the example two, as I said, I selected 0.65 and ended up getting the 58% porosity, right? So this is for that 0.65. If I select this to be 0.44, then everything in the Excel sheet changes. And this is where you get the input deck. Like you have everything copy pastable. Like you have this row that you have to copy paste into a dat file, and that's your input. I'll talk to you about further about this. I just wanted to show that that's that easy. Like everything gets done for you. Now, how can you select? Like, okay, this is defined for OPC. How can you select your own material? You might not have the same particle size distribution as mine, right? So if you see this green columns in the first two, I could hide the other calculation. I have just shown that they're here for just to show you how everything is done. But you can have the sieve size and the volume percentage written on each sieve copy pasted here. You can just simply copy paste your values. Delete everything that's not required in there. So that part is the green part. Everything is red, meaning like you don't touch it unless you know what it is doing. But what it's basically doing is like, again, those equations that I told you, equivalent volume of each for two. You can go into that and actually check the cells and know what equation is used and cross check if they are like, you understand what it is. So, and basically does the cumulative for the volume, all the things that you have to do personally by hand, the Excel sheet does for you. And when I said like this is the green arrow thing that you might have to change, but you usually will not have to. Meaning like if you see there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, there's no 22, right? By chance, let's say your material has a 22 sieve size, like you have a 22 micron size that you actually want to put. And this, you do not have to put personally. This will show you 22 if you have 22. If I change there something to be 20 less than 22 and greater than 20, you will get a 22 value. But it does not update this cell for that. So you might have to update this cell, copy paste from that Excel sheet basically. And once you have this, you can see like this is the total particle packing fraction, that theoretical value I told you guys about. Again, these are not correct. These are just for your assumption and for you to get an idea of like what I might need to increase. The end product is always going to be from the software, right? So similarly, based on this, there's material 2 defined. You don't need to do anything in material 2 because once you define the particle volume fraction in material 1, that's what it does. Because there's no material in material 2, it's basically 0, as you can see. It does this thing for 3, 4, and then it basically has a whole sequence where it has to generate input. Now there are few things you have to select here. Those are the many things. Like these are the material definition 4. Again, useful only if we do hydration. If we don't do hydration, for particle distribution, you could select everything to be 1 and you should be okay. The best part will be like on visualization part, if you do select different material numbers, you will get different colors. So you will kind of get idea of like, okay, this is my particle for this is my particle for this. You will get that idea. Even not for hydration, then also it will be useful for that. This again, based on whatever you already selected, it's gonna define for you. Like the way I said, there were 15 pins, 17 pins. This one has 20 different sizes that is required to be kept there. This part, the green part that you see is like dispersion factor is basically how close do you want to your particle to be? Is there something repulsing your particle? Do you want actually to make sure that they are apart? Then you can actually play around with this. I think this goes from 0 to 1. Depending on the numbers, the particles will be placed closer or farther away. Again, calcium sulfate, the gypsum that you want, the type of hydrides and anhydrides percentage that you take. Again, useful for hydration only. Okay, I'm just showing you that for future use, at least you have an idea like, okay, if you want to use this software in the future, then you know that what's going on in here. So those are there. And these two are basically your output file. Like you can name anything, you can leave those names be like that, because these are the files that the build MS will give you as a microstructure file, and we'll use that to generate the images. So based on that, like this is gonna be your input deck, right? Just for the sake of this, if you copy this, you just open a notepad file now, paste it, save it as anything.dat. Just make it a dat file when you save it. So once you save it as dat file, I think you already have it with you for this. But once you have it, save it as dat file, then you basically load that file and run the build MS thing. Like it's just a click of a button that you have to do. If you already have the file for example one, it's already the file is run. The images are also there in the example. The microstructure file is also already there. But if you just want to have a try, just choose dot dat, click the example one dot dat thing that we already have, and just run build MS. So what it does is like once you run build MS, it gives you these two output file. Like if you remember the cells where I said you have to define two files, it's written on the left side of it what the files are. What it does is like the am file that you was defined first gives you the actual microstructure. There's a p file that you can download, again not required here mostly. It has like the type of phase fraction, like what phase fraction is it, like in a cement, like let's say this is the C2S C3S, what it does after like actual hydration. Also we can see how the hydration products are formed, and all those things go into that. Those come into picture like only on hydration mostly, but again it for now it does create the p file also. So with these files, this is basically a executional thing, so you can actually see what it does, like what it runs. I'll run the file once I get over with this. Like I'll go around about it. I don't know if it's gonna be good enough zoom that you guys see, but at least if you guys run that, I can talk to you about how it's basically taking on the inputs and what it's showing up on the field. Once you have that, you basically download this am.file, and always I'll recommend you download it on a different directory, because you will generate images in the same directory that the file is. And if you download it in desktop, you'll have 100 images on desktop, which you'll have to manage later. So rather, initially itself, just download it on a different directory. And once that directory is downloaded, maybe I'll go through an example first so that we see it in action basically. And I'll then talk to like what the actual images give you. So this is your app, right? So you just go to build MS, click choose dot dat. Let me put this here so that I can see. Yeah, so for right now, I'm just gonna download the first example one dot dat. And I just loaded that file, example one dot dat. I just click run build MS. It does the thing, and basically if there's some error, it will say some error. And that error is going to be mostly when you select a particle fraction so high that it can't disperse the spheres. And in the end, like if you scroll down, you will see here that could not disperse by sphere number so and so, basically meaning that the spheres were so many that it can't distribute within the volume. So that way you just decrease the particle volume fraction, and you get the new input file for the reduced particle volume fraction. And like this is the menu. Like if I gave you this software without the input file, what you would have to do is like basically go into this each line. It says like enter the number of particle size that you have, enter the first class, what is the number of first class, what is the radius of the first class, what is the material of the first class, and it keeps on going like that. You have to input it manually if you do not use that. So again, chances of making mistakes are high, and chances of not understanding it also is high. Like in between, you might be like, oh, what did I put? What did I not put? You might means you can maybe you'll do 100 micron size for OPC, but there was 100 micron for size for limestone, which you already forgot. So those kind of things, this software, the input deck itself handles. And if you see like the way I told you, like at the end, once the particles are done, it basically selects the menu for outputting the file results. So once you select the output file results, you'll see here down there. Once you select that four thing that I told you, right? There was 4 and 5. 4 basically means that you are output asking the system to show the output of the file. Meaning like after that 4, you can see like, okay, the total count, voxel counts are that, of which you will see like there are altogether n number of particles for all this, and you'll see here like there's porosity. So I think this is the one for first example. So you have 72%. I thought I wrote 70%, but I think there's 72% is porosity on this one, and 26% is cement because it only has cement. But if you remember, I defined 0.05 for calcium sulfate, zero point 0.6 for hydrides, and for anhydrides 0.06. That those are like probabilities of a cement particle having a hydride, anhydride, gypsum particles. Basically, gypsum particles are present in cement to for setting and all those purposes. So defining them again is important for hydration. For the case of building microstructure, you can select those all three parameters to be zero, and the program will run fine. So it basically does the porosity. It selects it shows how many hydrates it formed, anhydrides, the number of anhydride particles it formed, and in the microstructure you'll be able to see like all this. Once that's done, the number 5 basically starts the program to save the files into the m underscore thing, the file name that we get. Once you have this, it exits the thing with the last. I think the last line on the system is 1, which basically makes asks it to exit and just give the files. Now you click download this thing, and you basically like it's shown on the next screen for me. You can even overwrite the already the file that was generated there in the example 1.5 for the MC150. Just overwrite it, save it, done. So again, this is the program already gave you, but you have a file that you can literally not read, not do anything, right? Like, what does it actually contain? You could get the porosity. You could again, there is a different system where we can load this and actually get the microstructure parameters and everything right away. Like we do not have to do the calculations. Like again, it's need to be included in the system itself. But right now, it is as a standalone system in a MATLAB code. But like again, a user needs to know what they created, right? Wow, you have to have a feel of like, oh, what did this program give me? Oh, I got a bunch of number does not give help, right? Again, that's where the next thing comes up, which is basically these two softwares. Again, these two softwares, because again, visualizing 2D to 3D is a very hard problem. Again, as I said before, I'm not a software developer. I try to develop what I can. I could not develop it 2D to 3D, so that's why I have to use this ImageJ open source software. And this is again, it's an in-house developed 2D visualization software because again, we had our own file that we particularly needed to be a certain way. I think this is the software is taking a lot of time to install. I don't know why. The basic knowledge I have from MATLAB is what I use to create this software. It kind of like installed okay on my system. I don't know if it's because like a certain system having MATLAB, it might be quicker. And for a certain system which does not already have a MATLAB installed, maybe it's slower. I do not know that for sure. But again, you guys can see if it installs quicker if it's a MATLAB, but hopefully everybody has installed it. So what this software does is basically it takes the file and it just generates the image slices. It does nothing else. It's just like you already have the file. You can select the file and it will generate you the images. So because it's set to be a 100 by 100 system, we have 100 slices defined right now. Again, in future, we are trying to make it such that you can define on the number of slices you want to create actually from it. For a 800 system, you could end up creating 800 slices, or you might want to create just 80, right? Like you might not want as much of a precision. Again, usually the more number of slices you create, it will be more precise because when you actually view a 3D view, it's projecting based on two slices, like it should be a sphere. which again, if you have more slices, it will be a more better projection than having lesser slices. Having more pixels will be even more better projection, right? So if you have this software open, what you can do is like, because it's set at 100, do not put any value other than 100 because it tends to distort the image. Then you can basically select the file that you just downloaded. Did I not get the? It's somewhere open now. Because I don't know. I have, oh yeah, it opened here, I guess. Yep. So the amp underscore C150 file that you already downloaded for OPC, right? You can just click that file, then it will start generating, and once it does, it just says processing complete. Images are saved in the same directory. You already had the images, so again, you will most probably, if you delete it, you'll know that the new images are created. Neither then it just overwrites the previous images. So you will not have, like, if you have already 100 images, does not mean you will have another 100. You will just, it will just overwrite the already existing image, because I think the way it's developed is like it does image 1, 2, 3, 4, 5, 6, and if there's already a file, it just has to overwrite. It will not do 100, 102 based on that. So once you have these images, let me close this. I think I might need it. I'll just put it on the background. So once you have this done, now you have all these images. This is for example 2. So you'll not have a as packed of a microstructure for example 1, because knowingly I kept more porosity in example 1. I think it's at 72% is porosity right now. So meaning like it won't be as jam packed as this is. Which again, if you go to example 2, this is, I think it's, this is example 2. It will be as jam packed as you see in the screen. Okay, you will get a general idea of it. Like the one thing that you should, again, it's kind of intuitive and not intuitive too. Like the particle that you see here are spheres, right? They are not circles. So spheres, if you cut at different sections, means like from a 5 micron particle, you might end up getting a 2 micron circle in the image. It's just because it's a different slice. The actual volume is the same 5 micron sphere it is. Now you cut actually at the center versus a side by, the particles look different. So sometimes you might see these particles look like, oh, I did not put as many of a smaller particles. Why are there so many smaller particles in a section? It's just like an outside portion of 5 micron. Think of it as like, right, in a system, if you have 15 micron, when you cut slices, it will give you 1 micron, 2 micron, 3 micron, everything within that. And there are very less number of these particles. So you will not see in most figures, you won't see those large particles. It's in the central figure that you'll mostly see. Once you have these images, again, for visualization, you can use another software. This is like a 2D visualization. You want it everything into one, and you actually want to visualize it. Then this is an open source software, very good. I would recommend the use of this software for a lot of things. Like again, it has a lot of function. You can actually do contrast images and calculate like the white areas versus black areas to calculate like porosities, calculate different things. Like it does, it has a lot of functionality. I'm just gonna stick to what I need right now. So I'm gonna show you how to actually load these images. So if you go to file, import an image sequence, because these are 100 sequence images, right? So you just can select that. And once you select that, for the case of visualization, I'll select example 2's result. I already have the results here. So I'm just going to select example 2 so that it looks more proper. Once you select the folder, you can just click on OK. You don't have to check any settings down there. It already updates that there are like this many files. And if it's not an image, it will not load. So you don't have to worry about it. So once that is there, uh, so we have to move this. Yeah. So you will see that the image is not as pretty as a sphere, because again with the 100 pixel size and 1 micron, 2 micron particles also coming in, few particles look slightly distorted. Again, the bigger the particle, it looks more better. Again, if you do this same thing with 800 pixel or 1000 pixel, it will be even better. Like it will look like more circular particles, meaning like it's again like the cross between like how bigger of a size do you want to generate, how longer do you want to simulate, and what you actually get, right? Like the this is for the process of demonstration, I just selected 100 because it's a small enough size, but big enough that I can actually make people visualize what actually is going there. So if you slide, you have all the 100 images loaded now. You can actually see the particle getting big and small. If you see, that basically gives you an idea that okay, this was not a smaller particle, it's just the slices of the bigger sphere that we see. Rather than that, this, there's even a better visualization on this, which is basically plugins, 3D, and volume viewer. If you go to plugins, 3D, and volume viewer, what it does is like it already loads the 100 slices and tries to create a generic volume. And the best part of this one is if you saw the slider there, right? One thing I'll ask you to do is like basically put this global alpha offset to maximum so that actually the posts look white and the other colors look completely as they are. It's in like 2D gradient and you have like global alpha offset. If you put that to maximum, you see the voids as white and the particles color as more dominant. Sorry? Oh yeah. So if you go to the thing, there's file, import, image sequences. And in that, you just have to select the, in the browse, you just have to select the folder. You just select the folder, it understands what the file inside is. There are already 100 plus one image file plus one actual input file, right? There are 102 files. That's the count. You see that 102. But because 100 of them are only image, it just ignores the two. So you don't have to worry about ignoring it. Just does it for it. You. So once you do that, once you load, it's plugin 3D volume viewer. Again, you'll most probably get like tutorial of how to use image a lot in online. Like again, this is a simple specific thing that I'm showing you here. It has a lot of functionality. If you start using it, you most probably end up using image for a lot of your activities. Like you will find that this is very useful tool to use. So once you have that, you see this volume, right? You see the distributions. Like this sphere was cut from this side because it has to be cut at 100. You see that those all the stacked images are such that it basically has that particle like cut all the sections kind of viewable. Like all the corner stops are like there are like corner edges and all those things visualized. If you see this sphere, it was cut from this side on this side also to basically fit in there. All those, and the way you had only slices in one direction initially when you load, right? If you have here, if you see this, you have slices in all three directions. This is your slice on, I think that's X direction. The middle one is your Y direction. You can actually have all those slices if you see. And even you can have the same slices on Z direction for this to visualize actually like how the particles are distributed and everything. You see the red color is defined for OPC. There you see some blue colors, right? I only defined one thing. But I did not actually define one thing because there were anhydrides, hydrides, basically gypsum, right? If you put zero, there will be only red. For calcium sulfate and all those things, if you put zero value, you'll only see red particles, meaning like there's only OPC. Again, because it's very important in hydration part of it, we have it defined. When I ran this simulation, I just kept the values there for OPC. So hydrates and anhydrides are present. Those are the blue circles that you see there. I think anhydrides are cyan color, not blue. So you'll see like two different colors for hydrate and anhydride. So this is basically to view, like to understand like what you actually generated, like what the microstructure looks like, what it looks like. Again, you can play around with the images after. You can do a lot of things, like you can have black and white, all grayscales and all those things, all different things that you can do. Again, I'm not going to go into a lot of detail into what you can do in image. Rather, I would move on from this. And I think, yeah, so these were the things as such, right? Like I think I told you up to this point, like viewing volume. Now I have a bunch of examples already set for you. I have tried to describe what the each example is in the folder name as much as possible. Again, there's a limitation of what I can describe also, I guess. So I've tried to be as detailed as possible. But if you see, this is basically the OPC particle only with high porosity. If you want to run a model that was like normal porosity, means like I already increased the volume fraction such that we have very less porosity. That is like the 58%. Because I have 56% volume already occupied by water, that's why I'm going at 58%. Now, you don't want to account for water. You just want to see like if I compact OPC, what happens. Then you can end up increasing the volume fraction more and more to a certain extent that the system itself says, okay, I can't generate anything more. I'm done. So that's a point where you can reach up to. So the next thing I told you, like despite me selecting 65% is the volume porosity is 58%, all those things, right? Why is that the case? Like we talked about all the volume packing and everything, like how we can pack the best we can pack everything into a higher volume fraction like 0.7, 0.8, right? The thing is like this software does not try to jam pack everything. It's a seeding mechanism where it selects some randomized seed, and at that seed it creates the sphere. Meaning like let's say for the maximum packing, what you have to do is like for a bigger circle, you have to touch the other circle right away on the side and keep on jam packing everything so that they are like touching each other and there's no gap, like literally no gap possible, right? This software does not do that. You can actually use the whole thing, but it basically has a randomizing kind of assuming that in the generic sense you will not have a compacted. Even if you do a concrete mix with the perfect particle size distribution, everything such that it could have jam packed into a very high dense system, it will not do it that for you because again there's randomness in nature, right? Like in actual computer system getting randomness is hard, so it does a randomness with a certain sequence, so you'll usually end up with the same value. You'll end up having the similar kind of microstructure. It will not differ much, it will not differ significantly, but it will not, most probably it will never give you like the jam packed volume, like where there's no literal gap. Like even if you open the images, you can see from the images that the gap between particles to particle, right? What it started with is just putting a, it opened here, but if you see each image, what you can see is like it started with putting a larger particle and started surrounding it with smaller particles. Now there was no space to put some particles also. Now let's say if I added maybe 1 micron particles, it has more space to put 1 micron particles, right? So I can add material to as like a 1 micron particle only, and I could keep on adding it till like it jam packs, kind of showing you like let's say you want to, you already have this OPC. Now how do you want to pack it? Maybe start with a 4 micron particle. Maybe you can get a material that you can sieve it to such that it just has 4 micron particle. You start adding those 4 micron particle into the system. Now again that jam packs it. Now start adding 3 micron particle, 2 micron particle, 1 micron particle. You can keep on adding to this particle. But again, the system already defined the particles to be somewhere, right? So it won't move that particle to add just another particle. Even if it has a zero point 0.5 gap there, zero point 0.5 gap here, it won't move it towards the right to put that 1 micron particle there. If it has a 1 micron particle left, space left, is only when it puts it. So it's kind of like a more randomized rather than a very jam packed, like what is the theoretical limit you can reach. It's not, it does not take it to the theoretical limit. So again, I have this as for the limestone one. This is one of the other printable mix that we had. This is L30, meaning like 30% limestone, 70% OPC at 0.35. So if I went with the calculations for this, I had the calculation somewhere. I had it written on a paper, but I had to basically in this, the volume percentage of water was 52%, I guess, 51, 52% by volume. Like in OPC, because I had to go 54, right? Because I had to go 0.4 percentage, 0.4 water binder ratio. I was at 56, sorry. I was at 56 percentage volume. With L30, I am at 52 something. So I again, for this also optimize it such that this is a general value that I selected initially. And then I kept on adding to it so that I can reach the limit where the software starts saying like, okay, I'm done. This is the maximum I can do. Now I can't put spares. Meaning like this is kind of like pushing the limit. I think I have still some limit you can add up to. Sorry, this is not the limit that I pushed to. Sorry, this is the limit where I pushed it up to 50 6%, 46%. Because 52, again, I wanted water to be there. So I'm just pushing it to the limit so that I'm reaching that volume fraction of water is still there, like the porosity to include that water. The one where I tried to push the limit is like, again, I have like OPC, then I have like OPC with, I think I put like one with three materials, also fly ash, yeah. OPC, like cement, limestone, fly ash. Then I have one with cement, limestone, fly ash, and an inert material, showing that with four materials. Like to generate this, you can keep on checking like the values. I can even provide you the values what I use to generate the actual input file. But again, you can keep on increasing the particle fraction. You generate the input file, you run the input file, you check the output. Now, if you keep on want to adding to the actual porosity, again, that's the thing. Like if you want to jam pack everything and see what I can get to the maximum, you keep on increasing till the software says like, okay, I can't put spares, any more spares. If you want to push it to the limit that you want porosity for water to still be there, you just move it such that you check the porosity. Like if you remember, I showed you at a point it just has a force selection and it starts giving you porosity value, solid fraction, amount, number of cement particles, number of anhydrous, number of limestone, number of inert materials, and all those kind of like in a list. So you check those values and you put it to a porosity such that you have the porosity to accommodate that water. This, I think, like, yeah. So 9, 10, 11, 12, 13, 14 is what I, when in the morning, like when aggregate packing, everything came up, I thought like I'll put some of the aggregate packing in there to kind of show you what it is like. I'll most probably get the paper, okay? I think I had this here. I did this sitting here listening to the lecture, so I do not remember all the values I kept here. So like if you see example 9, that's only 2 micron particle. Like again, just for example, I wanted to create that, and to show you for that, same for aggregate. So in that same folder, I created a file called for aggregate. It's the same Excel file that I showed you before to create the input file. But for the ease of showing you, what I did is like, again, you don't have to have all this particle size. Okay, you can just type to 100%. But whatever I already had, I just removed everything, and for 2 I put 100%. And when I put 100%, it creates me number of 2 micron particle sizes. Again, remember, it's not making the 2 particle sit side by side so that it fills up everything. It's not a 50 elements in a row, 50 elements in a column kind of thing. It randomly is sitting, meaning like it starts at a point, it starts distributing at random points so that it creates a microstructure. So it won't reach the maximum limit of 2 micron particle. But with the random seeding, you can start playing around saying that, okay, what is the packing limit I can go to? So we started with, I think this one starts with 55 and still could not do 55. So I had to go 50. So I started with a 50 particle. And this does not have anything else than the particles. So what you end up getting is 50% in the porosity itself when you actually run the build MS also. So if you put 50% and if you run this model, you'll actually get 50% porosity in the build MS. Now, similarly, for material, I think I did it material 1 when I did it. If you have the input file, if you run the input file, I think the input file has everything as material 1. I did not put it as aggregate. I just put it as different materials so that I can see the color gradient. I'll show you the pictures for it also. I put it as different materials, and for second, I just put like nearby. I did not have 4, but again, nearby 4 is fine. I think I put it at 3.99 something. So I put 100% as that particle. It calculates the equivalent volume for that, which again, because it's not 100, it's not exactly 4 micrometer. For a 4 micrometer particle size, it calculates a 99% equivalent volume. And again, it gives you the value, right? So for this, again, the initial itself did not work for 50. I had to go 50. I had to go 35% is packing fraction by the point I actually got it. Meaning like trying to show you like speed not be optimized, but for random seeding also, right? When you go larger particles, now you see that, right? Like the volume fraction is decreasing. Like you can't actually randomly distribute a smaller particle size to get more lesser porosity. You will have to have like at a point have different sizes so that it can kind of fit in. Because I did not have as much of a different sizes. I just selected 2, 4, 8, 16. And similarly, I have created like the the file that you have is like kind of towards the limit. If you increase it slightly also on the number of particles that is defined, because this is simply one single particle, right? You are defining only single particle. So you could end up just changing the particle numbers in the input file. If you see the input file, there's one single large particle size saying 920. So instead of 920, you can type in 940 itself and just run the model, because it's a single particle. You can end up seeing like how much can you push it to, like how many particles can you fit in into the system. So like that. Similarly for 8, similarly for 16, I did it. And like for this, I think it ended up being, you see, right, 2 per micron it was 50. For 4 micron I had to go to 40. For 8 and 16 I had to go to 35%. I had to have the remaining as pores, because again, like the random seeding did not allow me to put, I already put a 16 micron diameter particle, right? Instead, when you put 2, chances of putting a 2 is very high. When I put 16, the other 16 fitting between 216 is very low, because now you have to actually have 16 micron, the gap between two particles, right? So that way the porosity increases even just for a random seeding too. With this, what I ended up doing at the end is, again, I have this mixture defined, right? So I can actually play around with the 4 different particle size, 4 different proportions. Meaning like I do not want to have 100% of a 2 micron size. I would rather have 50% of 2 micron, 40% of 4 micron, 10% of 8 micron maybe. So for that, I think like the example 13 has like 70, 15, 10 and 5 percentage, which basically gave me a porosity of 55%. I think 50%, sorry. This again went to 50 percentage. Like it could go maximum for the random seeding could go up to 50%. Now I wanted to optimize it. Again, I did not have much time to optimize it. So another one that I tried is like a 40, 30, 20 and 10. So basically what I did was like I had everything ready. So I just typed in 40, 30, 20, 10. Again, I have not restricted anyone to put it to 110 percentage proportion, but I have put a check saying like total is equals to 100, so that nobody puts it like 120% is proportion, because you want to have it at 100. You don't want 20% extra in the same volume. So I just selected this. Like again, this is a random number I selected. I did not optimize it or something. For this way, I could go to 55%. I could go to 55% particle packing, and I could have 45% porosity. Kind of trying to give you a picture like, okay, with different sizes, you can actually push the limits. Like you can start pushing. Now, if I added 1 micron particle here, most probably there is a space to put 1 micron particle, right? My smallest particle right now is 2 micron. If I add another 1 micron, I have more space, meaning like I could push more particles in. And that will most probably end up giving me more volume, solid volume, because now, be it the system is the same. Think of it as such. Like maybe I can even load the picture and show you this, so that, yeah, seems pretty jam packed. But again, there are few gaps somewhere in between. Maybe like a 1 micron particle size might fit. Again, this is in terms of micron, right? Like let's say the smallest particle already was 5 micron. You could have fit in 1 micron, 2 micron, 3 micron, 4 micron. So those kind of things, like you can play around with the actual material you have. Maybe like again, you might end up sieving materials to actually get a certain sieve size, and you can play around with like how much percentage of a certain sieve size should I have to actually end up getting a better packing. How can I end up getting like the particles to be together? And again, this is in terms of picture. Now you have to have a number, right? You have to actually characterize this. You can't just have a picture say like, oh, I think like this looks better. And porosity wise also, like it's a different story, right? So there comes the whole concept of actual material parameters. Like define it in terms of number. Defining something in terms of number is always better. Like again, I think Professor Nathala went over all this, like what each represent. Each has a actual significance, why they are used for defining that generalized microstructure parameter. Again, I think there are 2 or 3 papers we wrote kind of like based on this. Like it's that important. Like it governs the yield stress, it governs viscosity, it governs for USBCs, like the strength that you can gain. Like with this microstructure packing being better, we could end up getting like the USBC strength to 160, 180, and all those things. So this goes into like packing model as defining the microstructure, even defining in terms of 3D printing. Like these could correlate into like there's a whole graph. I should have put that here. I think you would have seen that in one of the slide, but I don't know if you saw it today. I think it's tomorrow or something. So it's basically with increasing particle packing parameter, you have like a 5 square increasing, and with increasing 5 square, you have like the yield stress increasing. So it's kind of a indicative of that also. Like you have an indication of like, okay, what kind of yield stress do you assume this material to have? So all this these images are what generates this, like the number of particles per voxel, the Cn basically being the coordination number, meaning like how many particles are within a radius. Like now again, this is something you yourself can define. Do you want, let's say you have a 16 micrometer particle, means your radius is 8 micrometer, meaning r by 2 distance is 4 micrometer. The chance of the surface of that 16 micrometer particle being 4 micrometer from a particle is very high. A 2 micrometer means like half is radius is 1, half is 0.5. A particle being within 0.5 for that is very low. So basically that Cn kind of like accumulates that. Like if you have a certain size only, most probably for all particles you will have similar Cn. But because now you have like a distribution of particles, right? That coordination numbers give you like an average of like all particles, like how close are all the particles together to. Like is a particle like close by to the other particle in terms of their radius, not in terms of the overall volume, but like for a particle we are defining it in terms of that particle itself. So for bigger volumes, it could most probably end up being higher. Smaller particles, it most probably will end up being lower. And MCD being the distance between these particles. Like again, it's another parameter where it's surface to the particle, like the closest one. If you have high micron means between particles you have a lot of porosity. If you have the particles too close by, that MCD kind of goes down. So those kind of parameters are there. We'll end up kind of like developing this into the system itself. Like when you generate the microstructure, next step you can actually get these parameters right away. For different reasons, they are not still incorporated into the actual system. But the way we are using it right now, it's in terms of a MATLAB code. With I think I have not shared this with you because it's kind of like development itself, where it's a kind of a MATLAB that generates a GUI rather than a actual GUI being there. So the microstructure that you generated, right? What you can do is like just load the microstructure. I'll do this one. Yeah, you can just load the microstructure. This thing is like, again, we have defined it as a radius value also. The latest one, we have defined it as half the radius. So I am kind of limiting it to half the radius. Again, this program can be rewritten into defining it for like, if you want it at 2R also, you can define it at 2R. Everything will be defined at 2R. So similarly, if you have it defined at R by 2 versus 2R, obviously 2R will give you higher Cn, meaning like you will get a higher microstructure parameter value. But if you define it for 2R for everything, then they at least will be comparable between them. It will not be comparable. Like you can't define for a system at 2R and for another at R by 2 and say like, oh, this has a higher microstructure and this has a lesser microstructure. But again, to allow the users to actually have the freedom to define that value, you can end up like the maximum you can define is 0.5. Yeah, 0 to 0.5. So it's limited to 0.5. You can even want to like, okay, I don't want to do 0.5 also. I want to do 0.25 because my particles are too close. So I want to have some kind of differences. So you can define that. Again, the system size is 100 because again, the whole system size right now, everything is defined by for 100x, 100x, 100. So this is something in future we'll be able to kind of like define this. But for now, I have just developed it into such that right now it's definable, but we just can use 100 for now there. This voxel spacing is like again based on calculations for 100 by 100. These are like 1 micrometer particle is going to that kind of pixel size. So that's the calculation that we had from the voxel volume, and that is like set right now. If we have 800, there will be a newer number for that. What I'm thinking of is like we'll most probably put it like, okay, if you have this, you should have this value. If you use this, so kind of define it the other way rather than the spacing. We define the user to say like, okay, what's your actual particle size? And based on system size and particle size, the system itself loads the particle spacing. And once you have that, you just run the analysis. meaning like it scans the thing, it tries to read all the particles and tries to come up with all this value for you. Like you can't go into the picture and start measuring its distance, right? So what it does is like it automatically does that for a certain particle. It tries to find how many particles are within a certain radius. For a certain particle, it tries to see the distance between adjacent particles and see come up with the lowest distance. And what it does is like it averages it out. Like you have like 1,400 particles, right? If it was for a single particle, you could most probably end up going into the picture and calculating this also. But for 1,400 particles, 1,800 particles, 2,000 particles, you can't calculate it yourself, right? So what this software basically does is like calculates it for you, gives you the value output, and between like different particle parameters, like between this system versus that system, you could calculate the parameters and check like, okay, which system might be better. Again, it's not a established equation that okay, if you have a k parameter of 0.1, you should have a yield stress of 1,000. It's not kind of defined, but you can most probably assume that if you have a parameter of 1 versus if you have a parameter of 2, most probably your 2 parameter is going to have higher yield stress than the 1. So those kind of comparison you can have, like for a certain mixers, like can I incorporate some kind of aggregate so that I can get higher structural parameters, so that most probably I'll end up being printable plus being like more having more yield stress. So those kind of things is what we can play around with this. I think am I over time or done? So these are the kind of things I had for presentation. Again, if somebody has any question, I'm happy to try to answer them. Maybe I'll not answer all the questions, but again, I'll try to answer it to my best. And again, as told, hopefully sooner than later, this will be completely developed and anybody can download in their Windows system, not a Mac. I think we'll never develop it for Mac, but for Windows, they can download it, run it for themselves. It will be open source. I think right now we have the thing linking to Professor Nethila's lab page where we have the download link. So we'll update that. Like as the versions come up, we'll just update that and we'll keep on developing on this. Like again, there might be a lot of bugs which I might have not found it, right? With programming, always that's the case. So we'll keep on updating that. Once something is fixed, once some upgrade is there, it will go onto the system right away. You can download. Most probably what I'll try to do is like have a readme file. I think we don't have a readme file yet. We'll have a readme file where we can actually, again, somebody who has not actually seen this or who has seen this at least can go read that and kind of refresh their memory saying that, okay, I should have done this or done that. So we'll have that. And hopefully, like again, I'm not going to promise you a date, but again, hopefully sooner than later, you'll have the whole system. And again, I did not show you guys this, but what it does is like from this same am file, the am and p file that you have, this will have like build ms will have a input file for those, because here you don't have to do much. Build ms only requires one another file to distinguish the cement type and how the hydration happens. That again is a debload file. So you can load all three files and you'll end up getting the distribute ms output from there. That output will go to the hydration model and you'll get a hydration output from there. There will be some parameters you have to define in the hydration, saying that do you want like hydration for each day till 28 days? Do you want it at 25 degrees Celsius, 50 degrees Celsius? Do you want it? So those kind of parameters will be there most probably, but except that at least build ms, you should have it quicker, earlier than later, hopefully as early as possible. Yeah, so I think I'm done with my presentation. So any questions, anything in generic sense? So basically the output two files, these two files are generated for distribute ms. What distribute ms does is like basically tries to define it further into like what is C3A, what is C3S, C4S, AS, all these things. Like it tries to distribute everything again. And this go as an input. And that gives you a single output file which basically has that microstructure distributed now. You only had a particle, now that particle is also distributed into fractions. And that fractions now go into the hydrate ms, which basically gives you the hydrate ms has a lot of files. Like it has like is it 25 degrees Celsius, 50 degrees Celsius? Is it like certain days, certain things? Again, those will mostly be defined by the user, because this has been done in directions before. We know that what to expect out of it. the thing is, the app is not running it right now. So there will be a bunch of outputs for hydrate ms, and once you have the hydrate ms, you will see like they have the file actually has like hydration at this day at 50 degrees celsius, abatic condition, all those kind of things, those are there. So those will be generated by that. Right now packing only, like again we will develop future, like that's going to take a lot of time. Mhm. Yes. Yeah, so that part is what I forgot to mention. I guess this is a 100 micron kind of size, right? So you can't do a 4 particle aggregate right now. Yeah. No, meaning for simplicity, what you can do is like if you have a 2 particle size, you can assume that as 2 micron, and everything that is generated is in terms of 100 now. It is just scaling it down. So you can scale down the particles. I am actually using the size I need, but you can actually use the scale down size also here to generate those microstructure. The size. Sorry? Yeah, like as Professor Nethala showed afternoon, right? We had like this same thing was used in a different sense for aggregate packing for USPC, and we had like, so he showed like 60, 70, 0.7, those packing fractions that he showed are like basically kind of like developed with this build MS thing. It's not a software, that was like a C++ code with the file only. That's where it comes out. Like we had those done as such for a C++ code. So those are basically the output from here itself.
You can download it. So it'll have multiple functionalities you can do it based on particle sizes. You can base, I think you can do based on reverse also. Given a particle size of cement via limestone, whatever, what proportions will give me the maximum pattern tensor? I think you can do the reverse. If you want to do it and make sure that the reverse problem can be solved. So the organization can be made easy. But you see that, you see the complications and trying to make it simpler solve. It is very easy to explain it in slides. What is it actually developing in the form of it's not especially if you don't know how to put the right inputs, then you can take the jump.
If nobody has any other questions, we are gonna move on to quiz for the day. Yeah.